you make a level curve from each constant.
Have you done the homework yet? Have you done the homework yet? Okay, that's fine.
Is that right? Like you treat it like a stack. Because like if it's just x, it's a one-dimensional axis. But like if it's x and y, maybe like an x and y plane upon which the z value would depend.
Okay. And then what do you get? Yeah, what do you get?
That's just my guess.
Okay, so what's the graph? How do we graph a single variable vector valued function? Remember what those graphs turn out to be? Nick knows. Matthew, what do you think? A line? Always a line? Becca says a curve? Yeah, it's like a string of points, right? So you think of the vectors coming out of this function, or like in standard position, and like a laser light show, they sweep out a curve in space. It could be a line. It could be a line, right? The line was the first type of vector, single variable vector value function that we looked at, but then we looked at all kinds of different, curves, right? So that's what you get. You get a curve. And then what about a multivariable real valued function? What do you get for that? Taylor, what do you get for that? Remember from last time? And from the homework due today? How do we graph those? Okay, that's one way to do it. So you can, in x and y, right? You could put level curves and do a contour map. A contour map, that's one way to graph those. That's another way to graph those. Somebody new? Anyone start the homework yet? Anyone come to class on Wednesday? Surface, right? A surface. Surface is a way, is a depiction, right? For every xy ordered pair, you get a z, right? Every xy in value, you get a z. And then if you put all those points together, you get a surface in space, right? For every xy ordered pair, you have a z value, you plot those in space, and you get a surface. Because those are like functions of x, y, equations of x, y, and z. That's what we said, right? You have an equation of x, y, and z. We have our spheres and planes and paraboloids and cones and ellipsoids. Those are all single equation of x, y, and z. So now, as a function, we're just saying z as a function of x and y. So we're solving any one of those equations of x, y, and z for z, getting x and y is on the right, and that now is like a function of x and y. Z is a function of x and y. So we have a single equation of x, y, and z, and we said those were surfaces, right? Surfaces. Okay, so question?
So what happens if we had a function like f of x, y, and z?
Okay, so that like requires 4 dimensions because you have a fourth variable would be a function of x, y, and z. So then your independent thing lives in R3 now. So you're picking points in R3, and those are getting mapped to a fourth variable. So they call those like hypersurfaces. They're very hard to depict because we live in 3-dimensional space, and we work on a 2-dimensional surface. So it's like trying to show an image of 4 dimensions on 2 dimensions, right? So yeah. But that's what these are what they call hypersurfaces. Hypersurface. Like a higher, so in other words, higher dimensional surface. Okay, other questions? Yeah, please.
Just count with that. You can keep going with that into the 5th, 6th.
Yeah, right. So you can have a function of 7 variables, function of 10 variables. Yeah, Becca.
So like on the web work question 8
Okay.
would be that a fourth dimension function.
Right, they're asking you that they've got 3 independent variables and 1 dependent. But in terms of like using it, it's no different. You just have to have values for all 3. Yeah. But that's yes, it's an example of a 4-dimensional in that web work problem. Okay, so we were talking about again, these are the 4 representations of a multivariable. And we'll spend the most time on the 2 variable functions, right? So a formula definition, like f of xy equals the formula. The graph in R3 we said was, what kind of graph was it? Surface, okay? Learn it now, never forget. A multivariable function of two variables, a real valued multivariable function of two variables, graphs as a surface in R3. Okay? So then we took the traces for z values, we called those level curves, and we made a contour map. And you have some of that in your homework, some of those contour maps. We also talked about that at the end of class. And then a table of values. So these are for kind of most common representations of these functions, a multivariable function of two variables. Yeah, Samuel.
I have written in my notes that we're not supposed to let you forget about a cool animation.
Oh, yeah, shoot. Okay, so maybe I'll put you to work and I'll find it. Actually, two of them. I sat there for an hour in my office and forgot. All right, thank you. Thanks for reminding me. Okay, so now we're going to talk about the calculus of these multivariable functions. So rate of change. So let's just review rate of change in general. Okay, you're traveling on a highway. An app on your phone tells you that you're moving at 90 feet per second. And that's the rate of change of distance traveled in feet with respect to time elapsed in seconds, right? 90 feet per second is the rate of change of distance with respect to time. So what is the meaning of that rate of change? Okay, so it's the rate of change of distance with respect to time. What does it mean that it's 90 feet per second? 90 feet per second. Yes, sir?
For any change in seconds, your distance traveled will be 90 times as large as how many seconds in feet.
Okay. What's that? That's what it's called. So we're getting at the meaning of it. He said for any change in second. What about this? Every additional second means an additional 90 feet traveled. Is that a good definition? Is it true? Is it a true statement? Is it a good definition?
It could be bad.
How could it be better? Yeah.
dy equals mdx.
All right. So what does that mean, Ryan?
For any change in distance,
Any change in?
for any change in time, the change in distance is 90 times as large as the change in time.
Okay, so both these guys got it. Both these guys got it, right? So this is a true statement, but it's very narrow, right? It only tells you how far you go in a second. But this 90 feet per second tells you, doesn't it tell you how far you go in any amount of time? So how far would you go in 2 seconds? How far would you go in half a second? How far would you go in a third? See, a tenth. 9 feet in a tenth a second. How far would you go in any variation of seconds? 90 dx, right? So it doesn't just tell you how far you go in a second. It tells you how far you go in any variation of seconds. So you go 90 times dx feet in any variation of seconds. That's the broad whole meaning of this rate of change. Okay, so for any small change in time, the change in distance is 90 times that change in time. So this equation is what characterizes the meaning of this rate of change. Much better than just how far you go in 1 second. Okay, so for any small change in seconds, the number of feet is 90 times the change in time. Okay, so what does that mean for a two-variable real-valued function? So that's what we're talking about now. We're talking about these two-variable functions, or these multivariable functions. They have the form z equals f of xy. So what will we look at? We'll look at the rate of change of what with respect to what? So which variable with respect to which variable? Y with respect to x? Is that what makes sense to look at? Yeah.
Would you do x with respect to z and y with respect to z?
So rate of change of z. Yeah. So you had it right. You just flipped it. Yeah. So exactly. So we're going to look at the rate of change of our dependent variable, right? We look at the rate of change of dependent with respect to x or y. Okay, so we're going to pick one, right? And so this makes it a lot easier. So just pick what is the rate of change of z with respect to x, and then what is the rate of change of z with respect to y. So we actually get two rates of change: a rate of change with respect to x and the rate of change with respect to y. So that means that for any change in x, there's some rate that determines the resulting change in z. And then for any change in y, there's some other rate of change that tells the resulting change in z for that. So we call these partial derivatives. Partial derivatives. So there's a partial derivative with respect to x, that's the mx, and then there's a partial derivative with respect to y. So for a multivariable function of two variables, we focus on two different rates of change. So for the partial derivative with respect to x, in order to kind of analyze that, what does that require? We're going to hold y constant, right? We don't want y to change. We want to keep y constant, so we isolate how z changes just when x changes. So that means you're holding y constant. Does that make sense? Because if you let y change, then you don't know, if you let y change and x change, you don't know what the change in z is, how much is attributed to x versus how much is attributed to y. Okay, so we're going to keep y constant and let x change and then see what the change in z is. And likewise, for the partial with respect to y, we're going to keep x constant. And then see how z changes with respect to changing y. Okay, so common notations, right? There's, so for the partial with respect to x, you'll see this. So it's a Greek delta, Greek lowercase delta instead of d. So partial of z with respect to x, or if the function is called f, you could do partial of f with respect to x, you'll see that. Or just f subscript x. Those will all mean the same thing, the partial of the function with respect to x, and then partial of the function with respect to y. Okay, so we're going to then look at our we're going to look at these partial derivatives, these rate of change, through the lenses of the four representations. Okay, so first is, so the four are, remember, function definition, a surface in R3, a table of values, and contour plots in XY plane. Those are all representations of these functions. So in each one of those, we can talk about and kind of analyze partial derivatives in each one of those contexts. So we'll start with function definition. We'll come back to that one. We'll do this one first. Okay, so the displacement in millimeters of a point on a guitar string, x millimeters from the end of the string, and y milliseconds after the string is plucked is given by, this is an example function for one of these displacement functions of a guitar string. So does the situation make sense? Let's draw a picture. You've got a guitar string, say. And so x is the number of millimeters from one end. So we're talking about that point right there. And then y is the number of milliseconds after you pluck the string. And so what happens to the string? So this is exaggerated, of course, but it's gonna vibrate, right? It's gonna oscillate up and down. And so the distance from this center line position, say at x millimeters, so at some time, y milliseconds after plucking the string, or g of xy, I should. This is g of of xy is that displacement at that point. X millimeters down from the end, y millimeters after you pluck it. That point on the string has been displaced on amount g xy. So this function tells you what those displacements are. Does the situation make sense? So that's kind of a cool multivariable function. All right, so I'm going to find and interpret these. So actually, before we do that, let's find the partial derivative functions. So we'll start with the partial derivative with respect to x. So we could write like this if we want. We could also write those mean the same thing. Partial of g with respect to x. And so how do we find rate of change? Take the derivative, okay? And so when we're going to take the derivative with respect to x, so what are we going to do with y? Yeah, so you're going to, like we said, you need to hold it constant, right? You need to hold that y value constant. And so you're going to treat y as a constant. So pretend this y is like a 4 or a 10, but you'd still call it y, okay? So what would the derivative of this thing be? Nick?
3 pi hundredths cosine of pi x over.
So yeah, this says it's a function of x, and so the derivative of sine is cosine. So pi x over 100. But then, and then what about this? With respect to x, what is this?
It's just a sine.
Just a constant, right? If y is constant, then this whole thing is constant, and it's multiplied, so it just comes along for the ride, right? If it were added, what would happen? Rate of change would be 0, right? But if it's multiplied, it's just a constant multiple. It just stays along for the ride. So that doesn't change. But then we got the chain rule, right? So when you take the derivative of sine, you get cosine, but then you need the derivative of the interior by the chain rule, which is? Pi over 100, which is what she said. So 3 pi over 100 cosine times sine. All right, so partial with respect to y. Somebody new can do that for us. What would the partial with respect to y be? Chance, you think you can do that?
Would be 3.765 cosine
2.765 times cosine 2.765 y.
Yeah.
Okay.
And times the 3 sine pi x over 100.
How do you do? What do you think? Everything to do with the x, it's constant, so it's multiplied, so you just hold on to it. And then we're going to do now the derivative of sine with the chain rule. Okay, so you got those two formulas now. And so we want to find and interpret. Got those? Can I erase those? Anybody have a question? Okay, so now we want to find and interpret so taking x to be 70 and y to be 2.5. So I want to find and interpret the values of g of 72.5, g of x of 70.2.5, and gy of 70.2. So write those down, and I'll find those animations I was talking about. So write those down. Now you've got the actual functions for the partial derivatives and the function for the original displacement of points on the string. And so what you can do is get a partner, make a group of 3, and in terms of the calculating the number, just one person in each group do the calculations of the number and then share the numbers. But then in terms of the interpretation, everybody takes a turn interpreting. Okay, so when you get to these partial derivatives, There's a lot of detail that you need to include when you explain the meaning of the number that you get. There's a lot of detail. So it's not a quick, short 5-word phrase or something like that. It's a long sentence to do that in full detail. So I want to include all of the specifics related to these numbers. Is the task clear? Know what you're doing? So did you get this? I got these numbers. I got 1.43 millimeters for the first one. Negative 0.033, and the units would be millimeters per millimeter. Did you get that for the second one? Yeah, these are radians. So yes, for these sine and cosine functions are in terms of radians. Did someone get negative 0.033?
Yeah.
Okay, good. And then the last one, I got 5.43. And so, I think those have been confirmed over a couple semesters. So if you didn't get those, figure that out later. You can get the numbers later. So more important right now is interpreting these numbers. So what about the 1.43 millimeters? Veronica, did you interpret that first one?
Yeah, so we said that the first one was the displacement. And, so obviously it's the displacement of the string being like this 1.43. Well, we didn't actually talk, we were just talking about the different interpretations.
Okay, so the 1.443 millimeters, what's all the details behind that? So it's the displacement, but there's more to it. Which displacement is it? Which displacement is it? Right, so it comes from specific values that we plugged in, right? So this displacement has to do with these numbers, right? So what is this displacement? How do these numbers play into that specific displacement? Chloe?
Just 1.43 millimeters. That's the displacement of a point on the guitar string. That's 70 millimeters from the end of the string. 2.5 milliseconds after the string is plugged.
Right, good. So this is at 70 millimeters from the end. 2.5 milliseconds after it was plugged, you're going to find that point on the string is displaced 1.43 millimeters from the center line position. Okay, cool. So what about the next one? What does this number, negative 0.033 millimeters per millimeter, mean? Can explain the whole thing. Anyone want to give it a shot? Samuel.
I can give it a shot.
Okay.
I don't have any of the units on mine. So I wrote down the rate of change for the variable x, and I see the 70 and y equals 2.5 is equal to -0.33 with all else held constant.
Okay, and so let's talk about that in terms of the situation, right? So instead of when x is this and when y is this. So what does that mean for the situation? And yes, it's the rate of change, but what does a rate of change mean? So we want to apply what we were talking about earlier with the meaning of rate of change. Jared, what do you think? Give that a shot? Okay, so remember, let's go back to 80 feet per second. What was, or 90 feet per second meant what? 90 feet per second going down the road meant? What does that mean, 90 feet per second as a rate of change? Damien, what do you think? What was 90 feet per second?
For every small change in dx, it increases by 90 feet.
And so dx and it. So dx is a change in.
For n,
So our for a given change in seconds, the change in distance, right? Distance is 90 times that change in time, right? So that we want to apply that same thing to here, but now we got this other variable involved too, right? So given any change in time or any variation in time, how far you go down the road is going to be 90 times that variation in time. So how can we apply that same principle to this more complicated situation because we got another variable involved? Give it a shot.
Okay, so at 2.5 seconds, your rate of change of
displacement is negative 0.033 milliliters for every millimeter that you go
Right.
down the string.
And what does the rate of change mean? Yeah, so at 2.5 milliseconds, what can we say to make meaning of that rate of change? Matthew. It's a big day for you, Matthew.
Are you getting closer to the original point of like where the stream was, like it's oscillating back towards?
That's
the
true.
original
Yeah.
Position?
Well, it depends. So if it were up, if it's in positive territory, yes, it's moving back towards. But if it's in negative territory, it's moving away. So it's moving kind of in the opposite direction of whatever we call positive. So what does that number mean? Negative 0.033. Ronnie?
So at 2.5 milliseconds,
Yep.
the change in displacement is negative 0.033 times as large as the change in motion and the string.
Okay, good. All right, so now we're getting close. That was good. All right, so at 2.5 seconds, we could say given what? Holding 2.5 milliseconds constant at 2.5 milliseconds. Say given any variation in so here we are 70 millimeters down the string. And we're at 2.5 milliseconds. Right? dz equals mx dx. He's given a little change in distance down the string. The change in displacement will be negative 0.033 times as much as your displacement down the string. So and we are in positive territory. So yeah, so here we are 1.43 millimeters up, right? So what does it mean? If you increase your distance down the string a little bit, it's saying that the displacement will go down by 0.033 times as much as whatever little change in displacement you picked. Again, it's this right here. Okay, so now that that's said, can we do better on this one? Can we do this one? So what does it mean that the partial with respect to y is positive 5.43 millimeters per millisecond? Yes, sir?
When the retard is 70 millimeters from the end of the string, the variation of the displacement in millimeters is negative 5.43 times as much as the variation of time in milliseconds.
Okay, good. So yeah, so now we're going to fix the fact, we're going to fix that we're at 70 millimeters per second, and then what are we going to do? We're going to allow for a little variation in time this time. And then we're going to get a variation in displacement. And how much will that variation in displacement be? 5.43 times as much as the variation in time that you picked. Okay, so is everybody with me? This discussion has gone a lot better in past semesters. So this doesn't feel like we're getting it. Question, please.
Something I'm confused about is how you account for both of those rates at the same time. Like, is there something that tells us what happens when both if the time goes up by 1 millisecond and the displacement from the point on the string goes up by 1?
Yeah, that's next week. Yeah, we're just starting by isolating them one at a time. But yeah, that's awesome. That's a really good point, right? So if you let the time change and you look down the string a little bit, then what would your resulting change in z be? Exactly. That's a great question. But that's even harder, right? So we're just trying the easy part first. Just hold one of them constant and let the other variable change and see what the change in displacement will be. Okay, but these rates of change are the multipliers by your little change in independent variable that gives you the resulting change in the dependent, right? Holding the other variable constant. Okay, so we'll practice that on Monday again. We'll get a new situation and we'll practice saying it verbally what these mean. So for instance, one more time. At the time 2.5 milliseconds, given any change at the distance 70 millimeters, given any change in time, the resulting change in displacement on the string will be 5.43 times as much as the change in time that you picked. Doesn't make sense. Yeah, please, Ronnie.
With kind of the pattern here, when you're doing the partial derivatives, you're going to use at the constant rate.
The other variable you have to hold constant. So when we're doing the partial with respect to distance down the string, we're holding the 2.5 milliseconds constant. So at 2.5 milliseconds, holding it constant. If you change your distance down the string a little bit, the change in displacement would be the negative 0.033 times the change in displacement. And that's all at the instant in time, 2.5 milliseconds. Not changing that. Exactly. And then the opposite here. Here now we're holding the distance constant and we're letting time change a little bit. And this multiplier tells us how much the displacement changes for that change in time. Okay. Here we go. So let's practice a little bit more of the partial derivatives doing the formulas. So I told you the theme today was Batman. So here's the Batman function. Up there, ln of 1/3 x times x minus y squared to the 1/3. So we want to find the partial, write out the function for the partial with respect to x. And the partial with respect to y. Can you do it? So again, you're using all the same derivative rules that you learned in Calc 1. Chain rule, product rule, quotient rule, power rule, all those basic rules. But now you have another variable, and the one that you're not doing with respect to that other variable, you can. Okay, so maybe y is easier. How would you do the partial with respect to y? What happens to this natural log of 1/3 x? Just comes along for the ride, right? Because it's multiplied. So this is just a constant, right? If x is a constant, then this whole thing is a constant. So you just hold on to it, and then we need the derivative of this. How are we going to do the derivative of that with respect to y? So we got chain rule, right? Power rule on the outside, so it's going to be 1/3 x minus y squared to the times negative 2y. Right? So this, again, this is just like Calc 1 derivatives, but you got this other variable, and you got to imagine that it's constant. You're following all the rules, imagining that that other variable is held constant. So what about with respect to x? What do I have to do with respect to x? Well, what's the big picture? Is the big picture chain, or is the big picture product? Product, right? It's because we got one function times another. Then within the product rule, we'll have chain rule on this one, right? Okay? Barely. I'm just really... Okay, so derivative of the first is times derivative of the first times the second plus the first times the derivative of the second, which is going to be 1/3 x minus y squared to the times what? Just 1, right? So just the derivative of the inside now is the derivative of x, and that's just 1, so just there's nothing. So does that make sense? Taking derivatives. So you got to practice in your web work. You got to refresh on the rules, quotient, product, chain, power rule, all that stuff. But then just that other variable is you have to imagine it as do all the same things you would do that if it were constant. Okay, questions on that example, please.
So, for the FY one,
Uh-huh.
we got rid of x. We made that constant here. So why wouldn't it be the same for y squared in the first, like, for fx?
Are you talking here?
Yeah, because in the bottom one, x is 0.
You mean here?
Oh, never mind. I meant,
You good?
I'm good.
Okay. Best way to answer a question is to figure it out yourself. So it's great. Glad you talked it out. Other questions? Okay, so that's a function formula. So now let's talk about it in terms of graph. So going back to this. So here's a much easier one for partial derivatives. So partial of h with respect to x, it's like more like a polynomial, right? So with respect to x, derivative is 3x squared. So with respect to x, minus 4y squared, right? So that minus 4y squared is all the constant times x, and then plus 0, right? When you add a constant, that derivative is 0. Okay, and then partial with respect to y. Zero. Well, the partial with respect to y there would be minus 8xy. See that? Plus. Okay, so we did that a little bit fast, but because that's a little bit easier. Does anybody have a question? Are we good? Okay, so what is h of 1? We want to look at the point when x is 1 and y is 0.5. Partial with respect to x is? What would that be? Looks like 3 minus 4 times 0.5 squared. Is it 3 minus 1 or 2? I'm seeing 2. All right, and then h of y. All I'm doing is plugging in the 1 and the 0.5 for x and y and solving. So what's that? Minus 4. Okay, so
Is that 1/2?
I think this is, if I remember from before, I think it's negative 3.5.
Yeah.
When you plug x and y into that second equation, you get negative 3.5. So let's look at this now, and we want to look at this now in the graph version. So what would it mean in a graph? And what are graphs of multivariable functions again? Surface. Good. We learned something today. So here we go. So here's that surface of that function, h. And there's the point 1. Do you see the point on there? 1, 1.5? Does it show up? Black point right there? Okay, so the x-axis is coming out at us. So what would it mean to look at the partial with respect to x? We would be doing what? The partial with respect to x would be... Does that show up better? When we do the partial with respect to x, what does it mean? Letting y be constant. So holding y constant would be like putting a plane right through a y value, through that point. See that? And so then all we care about is changing x. And so when you put that plane through there and you change x, all you care about is what's happening on this curve for constant y. See that? That again. Better? See that? That curve right there? So that's where holding y constant. And so what do we look at? We're saying let x change a little bit, and what happens to z? So how much does z change for a given little change in x? For a little change in x, how much does z change relative to that change in x? What did we find? Didn't we find that it was 2, right? So the change in z will be 2 times whatever the change in x is, right? Holding that y constant. That's what that rate of change means. And you see that in the graph as what? Positive heading up at a ratio of change in z 2 to 1. 2 to 1. So for a change in x, z is going to go up twice as much. And it's positive, so it's heading up. What are we going to expect to see if we hold x constant? So based on the number that we got, what did we get for the rate of change? Negative 3.5. So for a change in y, what will z do? It'll go down at a rate of 3.5 times as much as whatever you pick for your change in y. So now I'm going to let y increase by a little bit. There's my dy. And so this is a constant x now, and here's the trace along the surface for constant x. So dy will be what? Negative 3.5 times dx, and that's what we're seeing there. We're seeing like that's about 3.5 times longer than whatever I chose for my dy. Sorry, dy. So if you go to the left in the positive y direction, sorry, go to the right in the positive y direction, you're going to head down at a rate of 3.5 z per y, right? Change in z per change in y. Question?
Shouldn't that be dz for the second line?
Yeah, sorry. That should be dz. Is that what you're going to say also? Yep, this is dz.
Yes, that makes sense.
So negative means as you increase y, z is going to go down, and then it's going to go down 3.5 times as much as whatever change you make in y to the right.